of our in-house LBM tool called Sankhyasutra Taral, and I will tell you what its salient features are, how you can use it, and through a demonstration towards the end, I will show you how to run simulations for any kind of CFD application that you have. Right. So, like I said, this is the agenda. So I'll describe to you how Taral is useful to you as a CFD tool to perform simulations where other solvers may struggle to give accurate results. I won't get into too much detail about the theory behind Lattice Boltzmann or the exact theory behind our solver, as all of this can be easily found online through published papers and other media. But I will describe to you when, why, and where you should be using Sankhyasutra Taral, where it's going to give you the most bang for buck. And like Ashwin said, you can interrupt with questions at any time. You can use the chat box or you can unmute yourself and ask me directly. Right. So, Sankhyasutra Labs is a company that specializes in high fidelity simulation software, specifically pertaining to application to a wide variety of problems in the domain of multiphysics. So this includes aerodynamics, acoustics, thermodynamics, chemical reactions, rarefied flows, and so on. And we are a team of 40 plus members that are working on constant development of our CFD tool. And we offer our tool. Well, our tool can be used as a licensed product or through simulation as a service. Right. So Sankhyasutra Labs started off as an incubation at the Jawaharlal Nehru Center for Advanced Scientific Research back into 2015. And the first couple of years went into making the core of the solver. And starting from 2017, we started performing projects with collaborations in industry and academia. So 2017 was our first major industrial project. And following that, in 2019, Reliance Industries invested in us. And subsequently, in 2021, we had our first major international collaboration for research with the US Air Force. So our technology is basically composed of two main tools. The first is our Lattice Boltzmann based CFD solver, which is used for most multiphysics applications. And for the specific use case of rarefied flows, where other methods seem to struggle and particle tracking based methods are show best results, we use something called direct simulation Monte Carlo method. And we run all our simulations through our in-house petascale HPC system. It's called Rudra, and it's the sixth largest supercomputing cluster in India. Right. So I guess all of you who are attending are familiar with CFD and basically the different ways that you can use concepts of CFD to solve fluid flow problems, right? And I'm guessing also that most of you have been using CFD in the traditional method, that is by discretizing the Navier-Stokes equation and then using either models or doing direct numerical simulations of that. So in the CFD community, the Lattice Boltzmann method has been growing in popularity, but some people still have the misconception that Lattice Boltzmann method is actually actually simulating particle motion to solve fluid flows. But even though Lattice Boltzmann method is based on something called the concept of lattice gas automata, which is a particle method, but in LBM we use a statistical description of particle interactions, and we model it based on something called the particle distribution function. So this is not exactly modeling or simulating the motion of particles, but it's more tangibly understood as simulating a packet of particles, and we resolve the probability of these particle packets traveling in some specific direction with some given velocity. So the solution in LBM is based on a discrete form of the Lattice Boltzmann equation, and a discrete form of the Boltzmann equation, sorry. And these particle distribution functions are the quantity of interest, and that is why we call it a solution of fluid flows at a mesoscopic scale. So the mesoscopic scale is something that lies between the microscopic and macroscopic scales. Now I told you about particle distribution functions, but that we're solving for those. But how do we recover our macroscopic quantities like density and velocity? So it's very simple when it comes to LBM. When you solve for the particle distribution functions, uh, you take the moments of this PDF in velocity space, and this will give you your macroscopic variables like density, velocity, temperature. And because we are solving at this scale, the equation of state is still valid, and you can basically recover your pressure based on the equation of state. Now, with RANS and LES methods, the solution is usually very sensitive to the model that you use. So, uh, if you're using RANS, especially, if you have a case where you have very large adverse gradients or something such, then there are very specific models that will perform well, and some that will not perform well at all. They'll give you very inaccurate solutions. So not all models are applicable to all problems, and choosing the right model and parameters becomes very crucial, and this comes from a lot of experience. Now, unlike traditional CFD, there is no turbulence modeling involved in our LBM method. So this means that we are basically solving for the actual statistical description of particles. And the aim with any CFD solution is to replace experiments as much as possible, right? Because experiments are very time consuming, labor intensive, and cost intensive. And let's say you take an example of a new product being designed. So with some method like RANS, even though it gives you a very fast simulation. You may go from performing 100 experiments to 10, provided that you are able to find the suitable model to use for your application. What our aim with Taral is that you go from 100 experiments to just a handful of experiments by making the simulations themselves more accurate, regardless of the application that you want to apply it to. So there's an adage that basically goes like you have to use specific horses for specific courses, and this is also analogous in CFD, which basically means you need to know which kind of CFD technique to use based on the objective that you want to achieve. So if your objective is just to get idea about what the mean flow is looking like or something like that, you might use RANS. And if your objective is, let's say, more specific, you want to look at flow structures and the details of how the flow is developing, maybe you want to look at boundary layer development and such, then you go for methods like LES, or if you have the resources with you, you do DNS, or you do LBM. So LBM is offered more as an alternative to LES than RANS, because RANS is going to give you very quick solutions, but they're not guaranteed to be very accurate. And our method is of a comparable scale to LES in terms of computational resources. And when it comes to accuracy, it is possible that you go to DNS levels without using any turbulence models. So the idea behind LBM, like I told you, is to simulate the uh, distribution of particles in space. So what we do is track the evolution of the particle density functions in velocity space, and discretization is done on a lattice that is made up of cubic cells. Now each cell will look like the example I have shown you on the right side of your screen here. So this is an example of something called the D3Q27 model, which basically means that each cell has 27 discrete directions along which your particles are allowed to move. And this is in 3D space. Depending on your requirement, there are a number of lattice Boltzmann models that exist. For example, you have the D3Q19 model where you will have 19 discrete velocity directions, or you can go to higher order models like the D3Q67 or D3Q167. Now, the basic algorithm of LBM is composed of two steps. The first is the streaming step, where particles are transported based on their particle density functions and the velocities. And the second is the collision step, where the interaction between particle packets is modeled. And particle collision is operated by something called the collision operator. And this collision operator is approximated by the relaxation to an equilibrium state or equilibrium particle distribution function. Now, there are some treatments two LBM that make them more stable, and I will get to a little bit more detail about this in subsequent slide. So, like I said, the entire idea behind LBM is to give you an alternative to conventional CFD that works, that makes your work more simple, right? And here at Sankhyasutra Labs, we've come up with a few innovations that make this even more easy for you. So the first thing you see is I'm describing the image on the top left here. So we use something called the entropic formulation of the Lattice Boltzmann method, which uses something called the H theorem. This H theorem is the equivalent of imposing the second law of thermodynamics. So basically, what this does is it prevents your solution from diverging towards an unphysical state. So it makes your solution very stable. And in addition to this, we use something called a crystallographic formulation of LBM, which is what you see on the top right. So most of the time, LB models are discretized in such a way that you use a simple cubic unit cell, which means that you have points, grid points at the vertices of your cubic cell. So what we do instead is use something called the body-centered cubic, because you already know that, I mean, it's fundamental physical stuff that you studied in high school probably, where BCC cells are more efficient at packing volumes. So you can see an example of that in the top right here with the two images of the discretization of a sphere. So what we do is, instead of replacing each cell with each simple cubic cell with a body-centered cell, we use a multi-grid approach, which basically means that we take the simple cubic cell grid of simple cubic cells and shift it by a specific amount so that we get the BCC points. Because you know that BCC points, the center point of the cube, is basically half a unit length shift in in both directions. So this will give us, when we use the multi-grid approach, we use only twice the number of points, but the discretization error is reduced by up to 6 times. It varies between 4 to 6 times. Now, to gather more detail about how BCC grids work or how entropic formulation of LBM works, you can refer to the references that are added in this slide here. Right. So the next thing that sets us apart from most of the other Lattice Boltzmann based CFD simulation software is that we use higher order models for higher order LB models for our simulation. So why does the requirement of higher order models even pop up, right? So it's common knowledge that the basic models of LB are not able to cope up with the requirement when you go to high speed flows. So let's say Mach numbers over 0.2 or 0.3, and this is when low order models start to struggle because they are not sufficient to capture the discrete directions in which your particles may travel, or the velocity that you assign in these discrete directions is not enough to capture the speed of the flow. So when you start using higher order models, it becomes possible to extend your range of accurate simulations to transonic or even supersonic flows. With our tool, we've successfully simulated high subsonic and transonic flows, as I will show you in subsequent slides. Now, in addition to all this, what ties it all together is that we have developed a novel data structure that is tailored towards parallel processing. LBM inherently is already quite suitable to parallel processing. And with the use of our novel data structure and something called the concept of structures of arrays of structures, we have made the task decomposition over a multi-node environment more stable and efficient, and hence this speeds up our computations as well. Now, coming to the details of our solver, one nifty feature that's on offer is automatic grid generation. So like I said, we use body-centered cubic structured meshes, and the algorithm basically requires users to give a maximum of two inputs. One will be the project level resolution or the courses resolution. So if you look at the image here on your screen, let's say this is your simulation domain and you have some body that looks like this, the one in red. So to generate the grid, I can give two inputs. One will be the size of the cells, size of the coarsest cells, and the second input will be the size of the finest cells. And by definition, the size of the finest cell, or by common sense, the size of the finest cell. I mean, finest cells will be used wherever you have disruptions in wherever you are going to have disruptions in your flow. So, for example, where you have solid bodies or something like that.
Yeah, I mean, Athreya, just relating to mesh, I think we have a very interesting question over here.
Mm-hmm.
So it says, is your software able to use cylindrical meshing, which is generally important if you are simulating a rotor to obtain similar meshing on all the blades. This is generally one of the problems faced by other LB tools, is what the users say. So I think you can just link it to what you're saying right now.
We don't actually offer cylindrical meshes. You can generate a cylindrical domain, but the mesh is not something like body fitted. This is a Cartesian grid. So all your cells are going to be aligned you have cubic cells which are aligned in the Cartesian directions.
Yeah, and I think if you have these body centered cubic mesh, that takes care of the curvature profile of the blades, which would generally require, say, a cylindrical.
Exactly. So like I said, most LB tools use a simple cubic structure for their cells.
Yeah.
But when you start using BCC with the same number of cells, you can refine. You can get a better resolution of your solid surface as well. It's still not the same thing as using a body fitted mesh, but it gives you better results.
Exactly. Yeah. Hope that answers your question, Chaitanya.
Yeah, like I was saying, we need to specify a maximum of 2 input parameters. One is the coarsest cell size, and one is the finest cell size. And the finest cell size is going to be right next to the body. That's by common sense. So it can also be that if you want to generate, so if you give these 2 inputs, you'll generate something called a multi-resolution grid, because there is a different cell size that you want to use here and at the extremities of your simulation domain. So the solver will automatically set up different levels. So in this case, you have 1, 2, 3, 4 levels. And what you're seeing here is not the cell size, but the interface of blocks. So a block is a collection of cells, which is the unit measure for what we transport to our processor. So each block is taken by one processor when you submit it on a multi-processor environment. So each block has 24 cells in each direction. So the actual grid that you're seeing here is not the full representation of your cell sizes. So anyway, refinement, again, it can be controlled by something called area brushes as well. So if you have some specific region in your simulation domain that you want to assign a specific cell size to, that is also possible. Now, if you don't specify the patch level resolution or an area brush, the solver will automatically take the project level resolution and set the same size throughout the domain. Now, because of our novel data structure, we have a very, very convenient thing where we see a linear speed up in the processing speed with an increase in compute resources. This is not usually the case with most solvers, because even though you might increase, let's say, your number of nodes from 2 to 4, you won't be able to simulate it in exactly half the time. Because of the optimization of our data structures to the parallel file system architecture, we are able to achieve something that is very, very close to linear. You can treat it as almost linear, as you can see from this graph here. So for this, as you double the number of nodes, your wall time for the computation also halves. Right. So I've been telling you what the solver is and how it works and stuff. But why exactly should you use it? What proof do you have that it actually works in a real world scenario, right? Now, due to the inherent stability and model-free solution of the Boltzmann equation, Taral is capable of handling complex aerodynamics flow problems where other solvers may struggle. So any solver can be judged by the ability to capture fundamental flow phenomena. So of relevance to aerospace and automotive flows and such, you can think of this as capturing free transition of boundary layers, or separated flows where you have very large pressure gradients, or even for bluff bodies, and cases like having dynamic stall. When you use wall models or other treatments, or you use modeling to capture scales that you're not actually resolving, your simulation might give you incorrect results altogether, because it's not suitable to the application that you're trying to use it for at all. Now, we have run our we have used our solver for a variety of different cases. For example, you see on the left side of your screen, there's a high Reynolds number NACA 0012 airfoil case, which was run at a Reynolds number of 3 million. And the specific problem here was to capture the transition of the boundary layer from laminar to turbulent. So you see from the uh, plot of pressure coefficient versus uh, location on the chordwise location in the chordwise direction, our solver is able to capture the suction peak and all the characteristics that you see in experimental results very well. And when it comes to simulation of separated flows, or similar prediction of stall, you see again from the center image and the animation that we are able to capture the details of the flow and the correct pressure distribution over the suction and the pressure sides for this NACA 0012 airfoil that was run at a Reynolds number of 50,000. And now I told you about doing dynamic stall and things like that, right? So our solver is also able to handle moving bodies very well. So the body can be rotating or oscillating or in some other kind of predefined motion. And you'll see from the plot of this lift versus uh, y-intercept that we are able to capture the hysteresis in lift for this SACON geometry that was published by NASA. And our results agree quite well with the experiments, especially in the for the peak, min and max of the CL that you're expecting. Now, all this was relating to more of a research kind of environment. But what about industrial problems, right? So you can have something like flow past an automobile, or flow for multi-rotor system, or something like a turbine blade in rotary motion, right? So you'll see from the images on the left side for the Ahmed body simulation. So an Ahmed body is basically a generic automotive body that is used as a benchmark to validate our solver. And you see from this streamline plot here that we are able to capture the vorticity and the vortex structures being generated and shed at the rear slant. This is not an easy task because it is highly dependent on the boundary layer growth here, and very dependent on the on capturing the correct pressure distribution across the entire surface of the Ahmed body. So our solver is predicting quite accurately where the vortex is forming and how it is being shed, and the entire recirculation region behind the Ahmed body as well. And when it comes to things like multi-rotor systems, so we have an example of the DJI Phantom 3 drone here. The simulation was run for a Reynolds number of 40,000, and the rotors are spinning at an RPM of 500. So you see that the tip vorticity and the interaction between the rotors is also captured quite well. And when it comes to simulating high-speed flows, for example, turbine blades in compressors or something like that, you see here that we are able to capture the local Mach number, even though it's going quite close to sonic conditions. It's all this is in the compressible range. Our solver does very well in capturing the local Mach number across the profile of the blades. And when it comes to multiphysics as well, Taral does a very commendable job. So we've simulated various things like store separation from an aircraft. So this becomes important when you have to deliver payloads, such as a military aircraft will be delivering bombs or something, or when it comes to civilian aid, you might want to deliver relief packages and things like that. So the scale separation problem is very complicated in the sense that it's hard to model and it's hard to exactly predict how the payload is going to behave and how the aircraft itself is going to behave once the payload detaches from it. And our solver is able to capture very well how the interactions are going to be and what kind of trajectories the payload is going to follow. And we've also done a few simulations on transonic flows, where so the one you see in the middle here is flow past the head of a missile. So you see that we're able to capture the shock quite well that's forming at the nose cone, and even the interaction of the boundary layer with this shock and subsequent generation of this detachment of it from the surface of the missile as well. And we've also simulated problems of relevance to industry now, especially relating to aeroacoustics, because it's a very important thing, aeroacoustics, when it comes to the current scenario in the world, because a lot of people have been complaining about noise, and every one of us is familiar with it, right? And now more and more governments are adopting very stringent regulations for this, so it becomes very important for product designers to actually give a lot of importance to these sound generation from their product. So the example you see here is of transonic flow over an open cavity, and the basic quantity that you want to measure here is the RMS of pressure at different locations along the floor of the cavity. What we also were able to match very well is the frequency and amplitude of the Rossiter modes, that cavity modes that are going to get set up. So yeah. And our solver is not just limited to single phase flows. We've also done some studies on multiphase, and we've seen that it works quite well, actually. So I've shown you a couple of examples here. One is of the canonical dam break problem, whereby you have a suspended fluid and then you model the interaction of this fluid with the other medium. Let's say here it was air. And we've done a simulation of cold flow in a piston valve, which has multiple moving geometries as well. And we validated our results with the spectral method, and the results match quite well. And it's also possible to do cases where you want to simulate rotating bodies and simulate mixing of two fluids, or uh, in general a multi-phase environment. What you see here is an impeller rotating in a stirred tank. This problem is very common in the chemical industry, for example, in the pharmaceuticals and such, where you want to create homogeneous mixtures and then use these to the package medicines. So yeah, these are all examples of the capabilities of Taral, and whatever we've been able to do so far. It's always a continuous development process, and we're always trying to better our results. But as it stands right now, we are already quite capable of tackling real world problems that are of relevance both to academia and industry. Now, the main reasons why you would want to use Taral as an alternative to LES that I mentioned earlier is that we solve the underlying physics without the approximation of turbulence models. This simplifies your job quite a lot, especially when you consider things like setting up RANS cases or something. You have to be very careful with the model that you're using, with RANS or LES or whatever it is. But with our solver, there is no question of using a turbulence model at all. It all depends on how you set up your grid, how well you've managed to refine the grid in terms of capturing the flow phenomena that you want to see. And all this is also simplified by the auto generation of a structured mesh. And we're able to handle highly complex and arbitrarily moving geometry. And we're able to capture accurate flow physics when it comes to incompressible, compressible, subsonic, and transonic flows. And all this is because we use higher order LB models. And the extension to aeroacoustics and other multiphysics scenarios is also quite simple for us. LB inherently is a method which lends itself to extension to all these scenarios. Now, why should you use Taral, right? Like I mentioned, there's no explicit turbulence model. And when you use such a method, it's possible to get to DNS levels of details. And whatever you are simulating is going to be representative of the fundamental physics of that problem. And because we use the entropic LB method, we guarantee that your solution is going to be numerically stable, unless and until you impose some very, I don't want to call it nonsensical, but sometimes users still do that. Unless you impose a very nonsensical boundary condition that gives you some infinite pressure or velocity gradients or something such, you're going to get a very stable solution. And we've optimized our data structures such that they lend themselves to better parallelization. And the automatic mesh generation feature is something that's very desirable when it comes to the efficiency of your work output. So you spend minimal time on problem setup and you use resources in a very efficient manner. And like I said, the LB models, I think everyone knows they're inherently transient in nature. So this also pushes itself in the sense that it's very suitable towards multiphysics problems. Now, where exactly do you use this solver? Like I showed you all those examples earlier. Most of them were related to transient and separated flows. So this is an area where a lot of uh, conventional methods struggle because you're either not able to capture transients very well, or you're not able to model the transition of the boundary layer from a laminar to a turbulent regime very well, or you're in general not able to predict the point of separation when it comes to adverse gradients or something such. But our solver handles all these problems very well, as you've already seen. And the entire reason to use CFD is to minimize the number of experiments that you do. So the logical place for Taral to fit in is before you go into experimentation. So it's called the before physics testing. So by running simulations with LB and knowing that your simulations are quite accurate, you can inherently skip some experiments that you would otherwise need to do just to verify, because of the accuracy that we guarantee. And doing CFD gives you much more insight compared to uh, very low level experiments where you use hot wires or something such. It won't give you a lot of detail about the flow field exactly. So that's another region where Taral would fit in. And I told you earlier that it's comparable at a scale to LES methods. So that's very important to note, because we are not a replacement for RANS. RANS is obviously faster. And if you have a problem where you don't want to spend a lot of time on compute, you just want some answer that is close enough, where it'll do if you have decent accuracy. That's not the kind of problem that we are focusing on. We are setting a new paradigm for CFD in the sense that we are giving out a model-free lattice Boltzmann solver, which is robust and has the capability to tackle real-life problems. So I will give you now a demo of a very simple CFD problem of flow past a sphere at a low Reynolds number. So I'm choosing a Reynolds number of 100. This is what my geometry looks like. I have a sphere of a diameter of 1 meter, and I have a domain which has these sizes. So it's 15 meters in the streamwise, 10 meters in cross streamwise, and 5 meters in the spanwise direction. I'll be imposing a uniform flow as initial condition, and I'll be using the no slip condition for the sphere walls and free slip everywhere else. And the inlet and outlet conditions are as you see here. So I will showcase the graphical user interface for our solver. Yeah. So you can access the Taral GUI by using this link here. It's called apps.sankhyasutralabs.com. And when you get to the web page, you'll be given a set of credentials that you can use to log in. I will log in with my credentials right now. And basically, it says that there's a end user license agreement. I urge you to go through it before just clicking this tick button and logging in. So once you log in, you're directed to something called the dashboard. Now, the dashboard is the area where you can see all the projects that you have created. So for new users, this is going to be empty. But I have stored a couple of projects here. And the way you create new projects is by clicking on this new project button. So let's say I said I wanted to simulate the flow past a sphere, right? So I will call my project as sphere flow RE. And I'll give it a description that will help me understand at a later point what I was doing with this. And once you click on create project, that project gets added to your dashboard as you see here. Now to actually start the simulation work, what you can do is click on this open workspace, and it will take you to the workspace of your specific project. So each workspace is unique to that project. And what you do first is get the geometry that you want to simulate. So there are two options. I can either import the geometry that I want to simulate, or I can create some basic shapes like sphere, cylinder, and box. Now I already have the geometry, so I'll say import. And the geometry that you import is going to be of the STL format, ASCII STL. So this basically means that you have a surface mesh that is made up of triangles. So once you click select, you see the details of the file that you've chosen to import, file size and all that. And to import it successfully, you have to click on this tick button which says import file. And as soon as the import is done, your geometry should be rendered in the viewer as so. And you'll also get a confirmation message. And you can access the details of your geometry here. So let's say I want to specify, I was telling you about multi-resolution grids, right? I'll set up a multi-resolution case for the sphere flow problem. And the way to do that is I say I want to set a resolution for this surface called sphere. And I'll say I want cells that are 50 millimeters in length. Because my diameter of the sphere is 1 meter, I want to use 20 cells per diameter. So I'll set a resolution of 50 millimeters. All the quantities that you enter in this GUI are going to be in SI units. And that's also displayed here. Unit system is SI. So the sphere surface is the only surface where I want to set the resolution, and I've done that. And you have controls to basically change the display properties like color and transparency and stuff. And the next thing you have to do is set up something called region. So if you go back to the model that I showed you here, we have three regions in this system. So one region is whatever volume is enclosed within the surface of the sphere. The second region is whatever volume is enclosed between the surface of the sphere and the domain walls. And the third is outside the domain walls. And what we want to do is simulate flow over the cylinder. So we will simulate only the cells lying in the region number 2 that we see here. So I will set up my case in that way. So I already have a default outside region set up for me. I say that the geometry that I want to set up this region relative to is this sphere with domain. And you can play around with this point or whatever you call this display point. You can set it according to the size that you want. It basically shows where this exact point is lying. And once so you have two kinds of uh, regions. So one is called simulate, and the simulate region is where you tell the solver basically that this is the region that I want to simulate, and whatever you set as vacuum is not going to be simulated at all. So if I'm setting up the outside region, I don't want to simulate anything outside the domain wall, so I'll say it's a vacuum kind. And now I'll set up the other two regions in the same way. So I have my fluid bulk. This is the region between the domain walls and the sphere. So let's say I do this. You see the point here in that golden yellow sphere. And this is of simulate kind. So I set it as simulate, I click save. And then I add the third and last region, which is the bulk of the sphere. Now 0, 0, 0 is already inside the sphere, so I'll just leave it as it is. So now I finished setting up the region. The next thing to do, if you want, is to set up those area brushes. So area brush is a region where you want a specific resolution to be applied. I don't want that in this case, so I'll just skip that. But if you want to, in your case, you can do it. So the next logical thing to do is set up or indicate to the solver what the material properties are that you want to use for your simulation. So by default, we have two materials, air and water. So if you click on that plus mark next to materials, this pop-up window opens and you can select the default material that you want to add. You click add and then your library gets populated with that material. And it's also possible to edit the material properties that are assigned to this material. For that, you have to click on apply. And basically air got added to our simulation. You go here and then you modify. Let's say I want it to be this value. So I edit it and I click save. So it says my changes have been saved successfully. So the only thing left for us to do is set up our initial and boundary conditions and whatever measurements that we want to save. So I said I wanted uniform flow, right? So I'll set up an initial condition called uniform flow. And I say I want to apply it only to the region that I want to simulate. I'll give it an initial velocity of whatever corresponds to my Reynolds number of 100. And I'll say I want to simulate at room temperature. So I set that up. So my initial condition is set. I got this green mark. And the nifty feature that we have with the GUI is that whenever you import or create a geometry, the list of boundary conditions that you have to apply gets populated automatically. So each face of these corresponds to one of the domain walls faces and the face of the surface of the sphere. So here I want to apply the no slip condition, which is the wall condition. Oh, something very specific is the from and to region. So the order in which you specify the from and to region sets up the boundary, the points at which your boundary conditions are applied. So the rule of thumb is that you set up the from region as the vacuum region, vacuum type, and the to region as the simulate type. So here for the sphere surface, my vacuum region is the sphere bulk, and the simulate region is the fluid bulk, and the surface is set up for the sphere, which is highlighted in red. So similarly, I'll set up the initial condition, inlet condition for my X-min face. So I go here and I say from is outside, to is fluid, and X-min is my surface, and I want to set up this velocity as the initial condition. I click apply, that's done. And then I go to Xmax, which is my outlet. So I'll click outlet and go to fluid bulk. And then I set the static pressure for 1 atmosphere. Now I want to apply the free slip condition to the rest of the walls, let's say. So I'll select free slip for the first one and I'll set it up. It's for Ymin. And to make it easier for users, what we've given is the copy boundary condition functionality. So if you go click on this copy button for the boundary condition that you want to copy, you can select the other boundary conditions to which you want to copy this condition. So you see automatically the other three also got populated with the correct surface as well. So now you set up your boundary and initial conditions. The last thing to do is set up your measurements. So measurements are basically simulation data that you are saving. So we can save three kinds of simulation data. One is probe, which corresponds to zero-dimensional data on any point in the simulation domain. And then volume corresponds to saving data on the cells. And surfaces corresponds to saving data on the surface that are set with no slip condition. Now there is a fourth kind of measurement called integrated quantities, which basically gives you the integrated forces and momentums on the surfaces that you select. So let me just set up the probe and I'll get to that. Let's say I want a probe in the wake. I'll call it wake_1. And I want to save these four properties, well, all of the properties. And I want the probe at the coordinates 1, 0, 0. And the sampling interval I want for my probe is 1 second. So data will be saved every second. I click save. It says my changes are saved. And you see my probe got populated here. And then I'll set up a volume measurement. I'll call it sim wall, let's say. And I only want to save pressure and velocity and density because I know that the temperature is not going to change very much and I don't need to give importance to it. And I'll say I want to save the state of the volume at every 10 seconds. So right now what we do is save the entire simulated volume. So you click apply and that also gets populated here. And let's say I skip the surface measurements, I'll save only the integrated quantities. So it gives you an option to save the integrated forces on these surfaces. And I have only set the sphere surface with the no slip condition, so only that is given as an option to me here. So I say I want to save. So all these are done. Now the last thing to do is set up my general simulation parameters. So let's say I want to run the case for a total of 1000 seconds. So I want to simulate the flow past this sphere for 1000 seconds. And because it's a very small case, I know that I won't need a lot of time to simulate it. Let's say I want to simulate it only for 15 minutes. So I give it 15 minutes and 0 seconds. And the number of cores basically refers to the number of processors that you want to use to run your simulation. And I want to use only 128, so I'll keep it at that. And like I said, project level resolution is the coarsest resolution. So if I want two levels, I'll make it as 0.1. And my reference length is used to calculate my non-dimensional quantity like Reynolds number and such. And another feature is for you to save restarts. So a restart is basically a saved state of your simulation domain, which you can use to resume from at a later point. So let's say your simulation crashes midway, but you have a restart saved. So you can start from that checkpoint instead of doing your entire simulation from scratch. So I don't want to save a lot of data because it might be unnecessary. I'll just say I want to save it 4 times throughout the whole simulation time that I have. So I click save and all of these parameters got saved. And to launch my simulation, I just click on this launch button. And it automatically submits a job to the simulation, to the compute cluster. And if you set everything up correctly, then you'll get this message saying the pre-submission check has passed. Now, it might take your simulation a couple of minutes to a couple of hours. So let's say your compute cluster is backed up with a lot of jobs. It might happen that your simulation is in queue and you will get the status message of your simulation here. So on our cluster, we have free nodes, so the simulation is started already. So it says running. Now to monitor the status in a very simple way, you can click on this thing called solver log. So this log will give you details about your reference quantities, about your grid, and the current state of the simulation. So now it says it's at t is equal to 0 with such and such performance figures. And it'll also tell you where your data files are being stored and such. Now, another way you can monitor is by going to this monitor plots. So whatever you saved as a probe will get shown in the monitor plots. And if you've chosen to save the integrated forces, that will also get shown. So the values that are displayed are whatever you've saved. So here I saved density, pressure, temperature, and all of these things. So all of them are displayed, and I can choose which to show and hide. And for forces, you get to see the lift and drag. So this is the x and y component. Now the simulation might go on for a few minutes. Or actually, it will go on for a minute or two. So in the meantime, I'll just show you something that I've already set up, and I'll show you how we post-process our data. So this is the same case. So you go to this post-processing window, and you can create something called a slice. This is to visualize your volume data. And the way to create a slice is you go click on this plus button. Say, give your slice a name, tell the post-processing tool what your slicing is done by planes, right? So you tell it the origin and the normal of the plane, and then you say the start and end frame. The start and end frame basically governs the start and end time where the data is being saved. So if you have, let's say, 100 frames, so the default value will be 0 and 100, and you can choose to save any number of frames between that. So I had some 400, I had some 70 frames. So it's given me a list of all that. So I can choose which frame I want to display and how I want the display to be. And I saved all the quantities. So let's say I want to look at the x velocity. And I saved this on a plane like this. So if I do this, and I can choose the color map that I want to use. So let's say I want to do cool to warm. So you see the flow is developing around my sphere. If you go to a later time step, you'll see that the flow is more developed. So this is basically how you can post-process using the graphical interfaces. So this concludes my demonstration. I hope I've explained things to you in a good enough manner that you understood whatever I've said, and any doubts that you had about LB or why you should be using Taral are clarified. But in case you still have doubts or any other questions, you can ask me now.